Welcome to Spring LIB.
Okay, we've got a pretty long multi-part question here. The first one is, which reaction mechanism is most likely in the case of a secondary haloalkane? Let's give an example. And a bulky hindered base. So let's give another example, like T-butoxide, for example. Sodium T-butoxide is a classic bulky hindered base. And they want to know what's the most likely mechanism. Well, a bulky hindered base, they're not strong nucleophiles, right? So it's not going to be SN1 and it's not going to be SN2, basically. Also, this is secondary, which isn't super favorable for SN1 or favorable for E1, right? If we've got a strong but bulky base, we're typically looking at E2. And so that's going to be the most likely answer, E2. All right. 2. Which of the following compounds is most likely to induce an E2 reaction with minimal competition from other E and SN mechanisms? We've got some options. We've got straight up methoxide. We've got T-butoxide again. Well, that's a good hint, right? That's a classic bulky base, and we just talked about how much of those favor E2 reactions. We've got hydroxide, and we've got Cl-. Well, the issue is that hydroxide is a very strong base, but also a very strong nucleophile. Chloride is not a strong base at all. It's a strong nucleophile, so these are right out. And now we've got methoxide, which is also a strong nucleophile. It's the second, compared to T-butoxide and hydroxide, it's the second strongest base here, which leaves T-butoxide as our most likely to cause an E2 reaction without competing substitution or elimination reactions. Okay. In an E1 reaction, the incoming base will attack A, the hydrogen on the carbon adjacent to the carbocation center, or B, the carbocation center, or C, the hydrogen atom on the carbocation center, or D, the leaving group. So let's discuss. So in an E1 reaction, it's definitely not the leaving group because, let's just give an example. The leaving group is already gone by the time the base comes in, right? And then we've got our carbocation, and we may have a hydrogen here, right? And so, is the base going to attack the hydrogen atom on an adjacent carbon? Yeah, that's what happens, right? That's how we get to our alkene. We still have our hydrogen here. The base does not attack the hydrogen that's on the carbocation, and the fact of tertiary carbocations, we don't have any hydrogen there anyway. And it's not going to attack the carbocation itself because that would instead be an SN1 reaction, right? That would be, if that happened, we would get this, which is not an E1 reaction. Okay. Finally, molecule of water is a bad leaving group, yes or no? No. H2O is a good leaving group. Right? We know that OH is a bad leaving group, and we often see that to induce OH to become a good leaving group, we first must protonate it to turn it into water with a positive charge. And then we often see that it is a good leaving group, and we can perform the kind of reactions we want to perform. Okay. So, no, H2O is a good leaving group.